Hi guys, this is question number 8.7 in our book Magd Wahab, and this is a case where the girder, it has a crane. The mass of that crane is 3.5 thousand, and the trolley and the girder of our traveling crane, it has a length of 10 meter. That girder length is 10 meters, and the trolley has a mass of 3.5 tons or 3.5 times per 3 kilograms at its midpoint, and it lifts a load of 800 kilograms through the steel wire of cross section area 900. So if I take this rope, the cross section area is 900 millimeter squared and 6 meters in length. The length of this rope, steel rope, is 6 meters. If the girder is fixed at both ends, so remember this is fixed case, fixed case, fixed beam. Alright guys, now has a flexure rigidity. EI is known as the flexural rigidity, where that is equal to 18 into 10 raised to power 9 Newton meter square. Use a model of a system with 2 degrees of freedom to determine two natural frequencies. Okay, determine two natural frequencies, omega n1 and omega n2. This is the case, and ignore the mass of the girder and use the Young's modulus of steel as 200 gigapascals. Giga means 10 to the power 9, Pascal means Newton per meter square. Now gentlemen, we have to find out a few things, the natural frequencies. So let me explain to you with reference to this plot. If you see here, I want to copy and paste here. Okay, let's copy and paste this one. This is easier for you to make an analogy. This trolley and traveling crane, I can model this like 2 degrees of freedom with the springs attached to them. So this mass M2, this mass M1, there is a steel rod or steel wire. So M1, this is M2, this is M1, and this is a steel rod which has okay, there is stiffness of that steel rod, steel wire, and there is the beam. So this is the beam stiffness. Alright guys, that's what we can find out from the table. So if I go over here, do you understand? And that beam is rigidly grounded. So this is rigidly grounded on the other end. So let me go to the Magd Wahab formula sheet. Yes, here it is. So if you see here, this case fixed beam. Now this beam, what is the stiffness? K1. This is my K1. This is K1. So let me rewrite this. This is K1, this is K2, this is M1, and this is M2. So this is M1, this is M2, this is K2, this is K1, and K1 is equal to 192 EI over L cubed. What is EI? 192 times 18 times 10 to the power 9 over L cubed. What is the length of this girder? 10 meters. Can you find out K1 easily by yourself now, right? And M1, what is the mass of this trolley? 35 or 3.5 tons. M1 is equal to 3.5 into 10 raised to power 3 kilograms, right? What is K2? The stiffness of this rod. There is a formula for that. If I go over here, that the formula sheet which I just showed you here, now it's a fixed, it's an axial bar, like an axial bar. What is the stiffness of an axial bar? You might not be able to see that, but I'm just giving you the reference. The middle column, this one, K, is EA over L. K2 is equal to EA over the length. E is given, area of cross section of that steel wire is given. Will you be able to find out K2 by yourself? So this is 3 into 10 raised to power 7 Newton per meter. This is 34.56 into 10 raised to power 8 Newton per meter. And M1 and M2 is given. They are both given 800 kilograms. So if you, this is pretty much similar to this case. So now if I leave this question as you can start from here onward. Can you start and easily complete this question at home from here onward? It is the same question, the same equation of motion in the matrix form. You just have to find out A, B and C and plug in this quadratic formula, and you can find out the two natural frequencies, which is the required question. Any question about it?